Okay, now we are ready to add some muscle activation and contractile dynamics to our musculoskeletal model so that we can have a muscle that's actuated by muscles rather than forces that we arbitrarily specify, and can then generate forward dynamic simulations that are under the control of muscles. Before I do that, I'm going to go to my parameters for muscle kinematics that I just defined here, and I'm going to reorient them a little bit. I'm going to parse out these parameters a little bit more specifically into vectors that are going to contain a value for each one of these coefficients for each muscle in my model. So these first coefficients, remember those are my neutral muscle lengths, the length of the muscle when all the joint angles are 0. And then I'm going to pull out these coefficients that I generated for the moment arm, or sorry, for the muscle length of the glutei to the as a function of the hip angle. I'm going to pull those out and label them with A's. And if you're wondering why I'm putting brackets around this variable that has just one number in it, I'll explain in just a little bit when I finish here. And then similarly here, I'm going to pull out my other coefficients in my second polynomial that was defining my length of my vasti as a function of my knee angle, and label those with B's here and put them down here. Okay. For my A's, these values are going to be associated with my first muscle, my glutei, and I want non-zero values there because the angle of the hip affects the length of the glutei. The angle of the hip does not affect the length of my vasti, my second muscle, so my second element in all these A vectors is going to be 0. Similarly here, for my B parameters, which are defining my muscle length as a function of my knee angle, my first muscle, my glutei, does not cross the knee and its length is not affected by the knee angle, so I want zeros in there for the first element in all my B's. My second muscle, the vasti, does cross the knee and its length is affected by the knee angle, so I want my non-zero values there in the second element there for my B's. And we can label these things to remind us what they are. These are going to be moment arm, sorry, so just going to be polynomial coefficients for hip angle. And the B's are going to be polynomial coefficients for the knee angle. Okay. And then delete my old one there. Okay, why did I do that? That is because now when I go to my model function here, now rather than writing out line by line a length function for each of my muscles and a moment arm function for each of my muscles to each joint crossed by those muscles, now instead I can do this in a loop. Okay. So we're going to loop over all muscles. Now for this model here that only has 2 muscles, this isn't really going to save me a lot of time and effort and efficiency. But imagine implementing this for a much more complicated model, say a model that had dozens of muscles or even hundreds of muscles, and some of those muscles have non-zero moment arms to multiple joints or multiple degrees of freedom. So I could have maybe 100 muscle length functions here I'd have to type out, and maybe a couple hundred or several hundred moment arm functions that I would have to type out here. That'd be a very cumbersome, error-prone process and just not very efficient coding and just not good practice in modeling. So instead, it's better here to define these functions for length and for moment arms on a muscle by muscle basis here in a loop. So here I'm just going to redefine my muscle length for I here, where I equals 1 is my first muscle, so that's going to be my length of my glutei, and then I equals 2, my second muscle, my length of my vasti. I'm going to grab, for the current muscle, its neutral length, and then add to it the influence of the hip which looks like that. And then add to that the influence of the knee, which looks like that. And this is calculating my muscle length. Okay, so what's going on here? For my first muscle, which is my glutei, it's going to go to my parameters, and it's going to grab these first three values for A. And so it's going to compute this first line here with non-zero values in there for A. So it's basically doing the same thing that it was doing down here. However, it's then going to go to these values for B, but all of those values for that first muscle, for my first entry here in B, are 0. So it's not going to matter what the value of Q5 is, it's always getting multiplied by zeros here. So Q5 is not going to affect the length of the glutei muscle. Relatedly, when it gets to my second muscle, it's going to go to the A values here, and the second entry in all of them is 0, so it's going to multiply all these Q4 hip angles by 0 and not have the hip angle affect the vasti length, which we want. And then it's going to go to B here and grab all my non-zero values there in the second entry in all those B's, and multiply that by whatever Q5 is the knee angle, so that my knee angle is affecting my length of my vasti muscle, which is what I want. Okay, I can also do this for my moment arms. Here's my moment arm to the knee. That's going to be the derivative or partial derivative of this expression with respect to Q4, which is going to look like that. And then my moment arm, oops, sorry, that's moment arm to the hip, not the knee. And then my moment arm to the knee, R2, is the derivative of this length expression which with respect to Q5, with the negative sign out front, which looks like that. Okay, so now I have my muscle kinematics, the length of the muscle, its moment arm to the hip, and its moment arm to the knee, defined as functions of those same parameters from last time, but now implemented inside of a loop here, so that I don't have to compute it line by line for each muscle inside of my model. Again, for a simple model here with just 2 muscles, doesn't really save you that much or gain you that much. For a very complicated model with lots of muscles, this will save you a lot of time and effort and remove a lot of chances for making a data entry mistake. Okay, knowing my length, I am now ready to calculate my muscle activation and contractile dynamics. And that's actually pretty easy because I already did it. We already defined all that in homework number 1. So I'm just going to go over here and grab everything that we did on homework number 1, except for this update states part. The integrator here is now doing that for us automatically. And I'm just going to paste that in here and stick an end down there. So just to review here, first thing it does is solve the activation dynamics, basically compute how quickly the activation of the muscle is changing. And I'm going to need that rate of change in activation saved for each muscle, so I'm going to index that variable. Remember, activation, A here, was a state variable in my muscle model, so it's going to be a state variable in my musculoskeletal model. So I'm going to have two new states here for activation. Okay. Then I'm calculating my SEC length as the subtraction of my contractile component length from my overall muscle length, which I just defined up here. And remember, my contractile component, that was another state variable in my muscle model, so it's also going to be a state variable in my musculoskeletal model. With my SEC length, I can calculate my SEC force. SEC force I'm going to want to save for each muscle because I'm going to need it in a little bit. I then calculate my CC force. It was simply just equal to my SEC force. Figure out where I am on the force length curve, figure out where I am on the force velocity curve, figure out the velocity of the contractile component, and then we are good to go. Velocity of the contractile component we will need for each muscle, so let's save that. And then I'm actually going to compute my joint moments here inside the loop too. I'm going to take my zeroed moments and put those up here and call those my initialized joint moments, set them equal to 0. And then down here, each time I calculate a muscle force, I'm going to update the joint moment with consideration for that force. So this is my hip joint moment from muscle forces, and tau 2 with R2 is my knee joint moment from muscle forces. So for example, for my first muscle, for my glutei muscle, it's going to calculate a non-zero SEC force, and it's going to calculate a non-zero hip moment arm. So that's going to be a non-zero moment that gets added to my hip muscle moment there. For my knee muscle moment, it's going to have that same non-zero SEC force for the glutei muscle, but it's going to be multiplying it by a 0 moment arm because the glutei does not span the knee joint. So this contribution here is going to be 0, and the effect of the glutei force on the knee joint moment is going to be 0. And then other way around, but similar sense for my second muscle, my vasti muscle. It's going to have a non-zero SEC force, a 0 moment arm at the hip, so it's not going to affect tau 1, a non-zero moment arm at the knee, but it is going to affect tau 2. Again, here doing this in a loop doesn't save me much for 2 muscles. If I have 200 muscles, then it saves me a heck of a lot. Okay, and it's as simple as that to add muscles into our model. A couple things we still need to take care of here, a little bit of bookkeeping. We need excitations for each of our muscles. We have not defined those yet. We will also do that inside of the loop here. Let's do it right above activation before we see excitation the first time. So we'll calculate muscle excitation, and that'll be UI equals something. We will define this muscle excitation as a function of time from some set of excitation parameters, UPARs, that we haven't defined yet. So this would be some set of parameters that gets passed to this function globally that then defines the muscle excitation as a function of time. We haven't done this yet, but we'll do this when we start actually performing simulations with this model. Down here, the very bottom, sorry. Down here, where I output my state rates, my rates at which my model states are changing. Previously there, I had the generalized speeds, which is how quickly my generalized coordinates are changing. I had my accelerations, which are how quickly my speeds are changing. And then I need to tack into here my activation rates and my CC velocities to tell it how quickly my new states are changing here. Okay, I'm going to make one more small change here to my model. I'm going to add a pennation angle to the contractile component. We previously did not have that. We had a contractile component that was exactly in the same line and direction with our series elastic component. To remind you, a pennation angle is this angle phi right here. It's the angle between the direction of the contractile component and the direction of the series elastic component. I'm going to add that to our model here because the OpenSim model that we are going to end up grabbing a lot of the parameters for these muscle models from is a model that has a muscle model with pennation angles. And so if we don't include pennation angles in our model here, then the parameters that we reference from that other model that does have a pennation angle may not jive with this model very well. We're going to do this by entering in a calculation of the CC pennation angle here. And how do we do that? The pennation angle is a dynamic variable. It changes with time in the model here. And in particular, it is a function of the CC length. Now, why is it a function of the CC length? Typically, the assumptions that we make here are that the CC is constant volume and constant thickness. Constant volume means that the total volume of contractile material here in the muscle is constant, is it's a fixed value. The material may change its shape, but the total amount of material, the volume of the material, assuming constant density, is not going to change depending on the activation of the CC or the length or velocity of the CC. Okay, so we're assuming that the CC here is constant volume. We're also going to assume that the CC is constant thickness, meaning the dimension of the CC that you can't see in this 2D page here, the dimension going in and out of the page is constant. What that allows us to do is then basically assume that the area here of the contractile component in this plane is constant, meaning that as the contractile component elongates here, then the pennation angle needs to get flatter, and as the contractile component shortens here, then the pennation angle needs to get higher, such that the total area of this page taken up by the contractile component is staying constant. We implement that in code by knowing a reference pennation angle at a reference length of the contractile component. And that's typically, that reference pennation angle is going to be a variable q naught, which is the pennation angle when the contractile component is at its optimal length, L naught. And so mathematically, what this constant volume, constant thickness assumption would look like is that the sine, or the CC pennation angle, or sorry, CC length times the sine of the pennation angle is constant. And L naught, the optimal CC length here, will be indexed because there's a value for each muscle. And similarly, the pennation angle associated with that optimal length is indexed. It's got a unique value for each muscle. I'm then just going to take this expression here and solve it for the actual dynamic pennation angle Q. So I'm going to divide by LCC. That gets me sine Q. And then I'm going to take the inverse sine of both sides. And that gets me Q by itself. Okay, how does this change the remainder of my muscle model here? A few small changes here. The length of the whole muscle is now no longer the SEC length plus the CC length. It's the SEC length plus the cosine of the CC length. So SEC length is now muscle length minus LCC cosine Q. And similarly here, my SEC force is no longer equal to my CC force. It's equal to the cosine of the CC force, the fraction of the CC force that gets expressed in that horizontal direction. So FSEC equals FCC cosine Q, or in other words, CC force equals FSEC divided by cosine Q. Okay. So just an aside here. Now we're finished with implementing the muscle model in the code here. We just need to define the excitation as a function of time, and then give it some initial conditions here for the CC lengths and activations, and we are good to go. Just an aside to finish up here. It looks like the pennation angle here might be a bad thing, right? The larger the pennation angle, or the more vertical the contractile component here, the less of that contractile component force gets expressed on the SEC and gets used to contribute to those joint moments and to actually move the model. So it looks like having a large contractile component pennation angle here can be kind of an index of inefficiency, like it's wasting some of the force. That's true. The larger the pennation angle, the less of the contractile component force produced by activation of the muscle actually gets expressed on the SEC and actually moves the joint and the musculoskeletal model. But there's also a good side to a pennation angle. The larger the pennation angle, the slower the CC can contract for a given change here in this S dimension, or for a given change along the length of the whole muscle. So having a large pennation angle there actually lets you produce CC forces at a larger range of fast changes in muscle lengths here, at larger ranges of fast whole muscle contraction velocities here. Okay. So in other words, with a larger pennation angle, you could contract the muscle at a faster speed and produce the same force at the CC and the same activation level as you compared to producing that same force with a smaller pennation angle at the same contraction velocity. You need a bigger activation. Now, less of that force would then get expressed on the SEC because the pennation angle would be larger. And so it's one of those things, like many things in modeling in general and muscle modeling specifically, where if you want to know, well, is a big pennation angle good or bad? Do I want a big pennation angle or a small pennation angle? Depends on the goal, depends on the question. If you want a lot of SEC force, then maybe having a big pennation angle is bad. If you want slow CC velocities, then maybe having a big pennation angle is good, and whether one's a trade-off for the other, or one wins out in the end, these are all highly nonlinear functions, so it's kind of hard to say as a general rule whether pennation angle is good or bad for a specific case, let alone for a general case. But again, we're including it here as a common element that's included in many muscle models, and because specifically the source model that we will use to parameterize a lot of these muscle model terms in here comes from a muscle model that has pennation angles. Okay, that is enough for that one, I think. We will next time grab some parameters to fill out our parameter script here to include the muscle activation and contractile dynamics parameters. We will define a excitation for each muscle as a function of time, and who knows, we may actually run an actual muscle actuated simulation. So we will see you next time.